Okay, that's good. So let me start by thanking all of you for taking time out of your day for this webinar. I'm Karen O'Neill. I'm the director of Green Bank Observatory. The Q&A feature, and we'll get those questions to our speaker. So with that, I'm going to go ahead and get started. So the agenda today is I'll give you just a brief update on what's going on with Green Bank Observatory and the GBT. And then we'll go on to the highlight of the afternoon, which is a talk by Rachel Friesen on the understanding the evolution of star-forming cores and filaments with part of the GAS survey. So Green Bank Observatory, what's going on? So COVID cases within the state of West Virginia are on the decrease right now. We're at about 3%, which is kind of where we were most of the summertime. Of course, masks are required indoors as they are throughout most of the country, much of the world. County cases themselves, the county's been doing fairly well, and the number of cases has gone down. Although next week schools are going to 4 days a week, so that'll double the number of students, and that'll probably have an effect on the cases in the county. The observatory itself, of course, remains in full operation 24 hours a day, 7 days a week. That's been going fantastically. All of our site protocols are working, and we continue to have had no cases of COVID that have been spread through the workplace. We are, of course, at the beginning of high frequency season with the GBT, which is always an exciting time. We're working on our new pointing model. This is a standard process that we go through every year. We've got the Argus and Mustang arrays up on the telescope now. And so fingers crossed, the weather will go well this winter, and we'll have a great 3 millimeter observing.
Filaments that are at the highest range of the column density. So these are the regions where you have this supercritical nature. Cores outside of filaments appear less likely to be bound. And in fact, also stellar clusters are often found at the intersections of filaments. So this idea predated Herschel. Phil Myers talked about the hub filament structure of a number of star-forming regions in 2009, but was also highlighted in Schneider et al. And also probably a number of papers, which I'm not mentioning here. So what does this mean? Well, this filamentary picture suggests that filaments are important in driving material to accrete and increase the amount of material available for star formation, perhaps in clusters, but also cores along filaments should also be being able to feed off that reservoir of material in the filaments. And so some of the open questions are, on what scales are clouds and filaments stable against gravitational collapse? How does the cloud environment influence the evolution of the gas? Do dense filaments, do they actually do this channeling of gas through flows and infall and accretion, as is suggested by continuum maps, but cannot be investigated without the kinematic information? And for also, how does the turbulence dissipate? How do you go from a turbulent cloud to a more quiescent filament and core? And how does the angular momentum of these structures evolve from large to small scales? So I won't be able to talk about all of these questions, but these are the questions that motivated the GAS survey. And so we really needed kinematics to kind of expand and continue the analysis that the continuum surveys, the rich data sets that they provided. So that's like I said, the motivation for the Green Bank Ammonia Survey, which is a large project to map the dense gas in all the northern visible Gould Belt clouds. And we were targeting regions above an AV of 7, which tends to be an observed threshold where you tend to find these high column density filaments, and also where star forming cores are more likely to exist in these clouds. And overall, we mapped an area of about 3.7 square degrees in roughly 10 different nearby clouds. And so you might ask, why ammonia? So for those of you who are not ammonia-holics, the ammonia is very useful in these regions. It is formed and excited at moderate density gas. So we're looking at gas that is at a higher density than you might trace with CO and its isotopologues. Also, it has this hyperfine structure, which really allows a precise determination of the excitation and hence the opacity and the column density. And you have multiple inversion transitions in the band at around 1.3 centimeters, and that are closely spaced in frequency and allow direct measurement of the gas temperature, which can then be compared with the dust temperature and used in these stability analyses. So on the top right, I'm showing you an example of ammonia 1,1 and 2,2 inversion spectra. And you can see the hyperfine structure and the fact that we detect both of those lines. In addition, we traced a few carbon chain species that are within the available range that you can cover with the Vega spectrometer at GPT. So the flexibility of that allowed us to target not just ammonia, but some other lines that trace kind of different chemical conditions. So the first data release was published in 2017 with 4 different regions, and the full data release is in preparation. And I also want to highlight that there's a few other GPT surveys on that kind of follow a similar set of lines, but examine environments in high mass regions, so more distant, and also in the galactic plane. So that's Keystone and the RAMP surveys. So these are all very complementary in that we're looking at nearby, more distant, and the galactic plane, and kind of can connect perhaps some of the analyses across the surveys. So very briefly, I just want to say that we were really benefited from moving from a single pixel receiver to the KFPA, the K-band focal plane array, which just dramatically increased our ability to survey star-forming clouds in lines like ammonia in a reasonable amount of time. So kind of starting from earlier studies which targeted cores and understood them in great detail, moving to some larger areas, and finally the maps like the one on the right towards Orion A that I'll talk about more. That's part of the GAS survey. So just to highlight a few of the kind of data sets that we have is looking at Perseus West. So the coverage here across that threshold of about an AV of 7 covers the major star forming regions in these clouds. And so you can see on the left-hand side is another Herschel 3-color image. And on the right-hand side shows the column density measured from the Herschel data. And this is work from Ayushi Singh in prep here at University of Toronto. And the white is showing you the region mapped, and the dark contours are showing you where we have a high intensity or high integrated intensity of the ammonia 1,1 line. And so you can see that the ammonia really traces those high column density features really well. And I should point out that even though the contours seem to be clustered around the highest column density regions, we actually have sensitivity to the line further off. And so with some different analysis techniques, we can really look at the ammonia emission and what it's telling us about the gas, both in the high column density regions, but also off those cores. And the other thing to note is that the distances for the survey of the clouds in the survey between 130 and 450 parsecs gives us a spatial resolution of something like 0.02 parsecs to 0.07 parsecs. So we're really resolving cores, star-forming cores that are about a 0.1 parsec all the way out to the distance of Orion. And here's another example, just focusing on an area in Ophiuchus, L1688 and L1689, where again, we can see that the column density of H2 and where we actually find the ammonia emission match up very well. And there's some really interesting structure in this particular region that we can talk about later. And finally, I'd like to highlight Orion A. My apologies for how pixelated that image looks on the screen. But this is the image I showed you before. So we're really able to map the entire integral shaped filament, getting down into some of the more clumpy regions which is broken up in the south. And this is the integrated intensity. But of course, we have the ability to fit the lines. And so along with the integrated intensity, we can get, we have beautiful maps of the velocities of the gas. This is the line of sight velocity of the gas across that whole region, and also the velocity, dispersion, and temperature. So what are we doing with all this data? So I'm just going to highlight a few of the papers that have come out of the GAS survey so far, and then I'll talk about our plans for kind of the future data release. So this is some work from Hope Chen, who used gas data identified in several gas clouds, cores with very low but not purely thermal velocity dispersion. So this is in fairly sharp contrast to the surroundings, where the velocity dispersion is, transonic or so. And these particular cores, which were identified just based on their very, very low velocity dispersions, were generally small. And possibly showed an extension of that line width size relation that we typically see for dense cores, where you have as you go to smaller and smaller sizes, the line width that you detect in those cores, the velocity dispersion of those cores drops to a value that's close to thermal, but not quite. These particular cores are not massive enough. They're actually quite a bit smaller than some of the typical dense cores that you would detect in other surveys, and are perhaps an earlier stage of evolution in the formation of cores and their evolution towards forming stars, where you are not bound by gravity, but instead these particular cores are bound by the external pressure in the region. And so I also want to point out Youngmin Sao's work in Taurus, where he also posited this progression from forming cores through a variety of mechanisms, possibly turbulent motions that are initially pressure confined, but eventually, if they gain mass, can evolve into being gravitationally unstable objects. And so kind of going beyond that on this stability question, moving into Orion and other regions in our first data release. This is a work by Kirk et al. And also point out a paper by Kerr et al. In 2019, where they looked at the stability of cores identified in continuum emission, but then adding in the kinematic information from the GAS survey and the kind of external bounding pressure from either the motions of the gas outside the cores or the overlying weight of the cloud. And so on the left-hand side is a JCMT map of Orion, highlighting where their cores are in the JCMT map. And on the right-hand side is a plot showing on the y-axis, the ratio of the self-gravity to pressure, and on the x-axis, the ratio of the energy densities, the gravitational, the kinetic, and the pressure. And what Kirk et al. Found in Orion is that most of these cores are in fact pressure bound. When you include the velocity dispersion of the cores, even though it's low, it's not purely thermal, and you actually are not, based on this analysis, bound only by the self-gravity of the cores. And like I said, we find similar results in the first 4 released regions in GAS, which is NGC 1333, Ophiuchus, and a region in Taurus. So here I'm going to just jump to a similar, somewhat similar analysis, but in the Keystone survey by Jared Cowan. So this is looking at MONAR 2. And this is zooming into the central region where Keystone mapped the ammonia emission from that central part of the star forming region. And so this is actually a map of the temperature of the gas rather than the integrated intensity. But you can see that the temperature of the gas increases in the center of the cluster and then is decreased to fairly typical values that you would find for low mass star forming regions in the outer edges. And so what they found in this paper is that there's a tendency for larger structures to appear bound via a virial analysis. And this is both in GAS and Keystone in the 2 papers that I've highlighted there. So you have this trend where some of the cores and clumps might have higher virial parameters, suggesting they are less likely to be gravitationally bound. And then as you go to larger structures, the virial parameters drop, suggesting that they are gravitationally bound. Now, in contrast to the gas cores, the Keystone clumps are more likely to be bound by gravity than we find in the previous results I mentioned, whereas in the gas clouds, we find different results. Another thing that we're working on right now is really disentangling multiple velocity components. And so the first data release really focused on a single component fit to the ammonia data. But what we're finding is that we have such sensitive ammonia maps that we can actually see where there are multiple velocity components in filaments or between the cores in the cloud and the kind of off-cloud regions. And so this is reminiscent of some of the work that's been done on fibers within filaments, where filaments in some cases appear to be formed of smaller, narrower fibers. And so even with the ammonia data, we can start to disentangle that as well. And so this is work by a number of grad students who have been working on different techniques to actually disentangle the ammonia emission, because given the multiple hyperfine components, this is a bit of a challenge. But what we can do then is have robust velocity gradient measurements both along and across filaments, and looking at the conditions in the gas between the cloud and the cores in the same tracer. And so on the right-hand side, I'm showing you an example of some of this work by Mike Chen in a paper just recently published, where he's looking at our data in NGC 1333. And on the right-hand side, I'm showing you where he's identified filamentary structures within NGC 1333. And then it's also showing you the velocity gradients measured along those, or the velocity measured along those different filaments. And you can see very clearly that there's velocity gradients along some of the filaments. But what Mike also found was that we see velocity gradients across the filaments, which can possibly be attributed to the formation or accretion of material onto these filaments. And so keep an eye out for additional work where over more of the GAS survey. And of course, I mentioned that we also have these carbon chain species. And so all of this data will be available in the second data release. And it's really interesting that some clouds we show very strong detections of carbon chains, like in Taurus, where you might expect, if you're familiar with Taurus as a region, and in Serpent South as well. So this is showing you, again, a Herschel image of Hellas Cloud 2, where we have a very strong filamentary structure and some star formation already occurring. And in the middle on the right, I'm showing you the ammonia emission integrated intensity and also the HC5N. So here you can see there's a well-known anti-correlation between the ammonia and the HC5N and the kind of brightest narrow filament on kind of the left-hand side. And what we're able to see, however, is that even with that HC5N, we're finding multiple velocity components in this particular filament. And this is work done by a student of mine who is analyzing the data with a decomposition technique that uses the spatial information across the map to try and find those connected components of the spectral line. So with this, we'll again, continue that analysis of understanding the structure of the filaments, but also their velocity information to understand stability and how they're forming and evolving. So just highlighted a few things in this particular talk, but of course we have future plans for data releases. So like I said, the full data release is in preparation and should contain the cubes and the moment maps for all the observed regions. So that's including the ammonia, but also the carbon chain species where detected. And then the property maps from our analysis, from our single component fits to ammonia and from our single component fits to the carbon chain species. So this is a rich data set for targeting higher resolution towards the really actively star forming regions, the high density regions with VLA and ALMA, and also looking at higher density tracers, for example, with the current Argus instrument at 3 millimeter in the GBT, or with a future Argus 144. So just to summarize, these large multidimensional surveys are needed to test predictions of, or these models of dynamic filament-led star formation. And the GAS is a legacy survey, and we have publicly available data and more data to come, but also our analysis tools are all publicly available. And so we will have a full data release coming soon. In the Gould Belt, some of the results we are finding is that larger ammonia trace structures do appear to be unstable by a virial criterion, but a lot of the cores in the nearby clouds are predominantly pressure bound rather than gravitationally bound. And the identification of droplets may represent an earlier evolutionary stage as you move from the formation of cores to something that is actually gravitationally unstable and forming stars. And finally, I just wanted to point out that ongoing GBT surveys really link star formation regimes across the galaxy. So there's a lot of complementary analysis that we can use and really build on to understand star formation in nearby low mass regions and high mass and more distant regions in the galaxy. So I will end there and take questions, and thank you very much for listening.
Thank you very much, Rachel. Please submit questions if you have them in the Q&A box, and we have several already. This first question may be more appropriate for GBO staff, but you're welcome to answer it, Rachel. It's how stable is Doppler velocity correction at the GBT in meters per second if you observe the same object in the same position after some time?
That's an interesting question. I have to say we have resolution of about 0.08 kilometers per second. And I don't recall ever seeing any shifts that are obvious in the data. So I believe it's good, but I couldn't give you a number.
I think that as the technically we have a velocity stability that is probably measured in centimeters or even smaller. I mean, it's the frequency stability. Anyway, we can deal with that offline. Here's another one. In the multi-component analysis, could some of the secondary components be due to outflows or other processes different from filaments and fibers?
Yeah, certainly that's a great question. So we're, really in earlier stages of analyzing on kind of a large scale, I guess the presence of these multiple components across our whole data set. Certainly, we have to investigate other sources of these multiple components. Yeah, it's not entirely clear if it's always fibers or if we do have secondary components from outflows. I will say that usually ammonia, particularly the 1,1 line, it does not tend to trace outflows. But certainly near a very active star forming region, it would have to be something we would have to examine.
Here's another question. Are the cores showing the same velocity as the filaments?
Yeah, that's another interesting question. So I think we're still working on doing a detailed comparison of cores versus filaments, but I can point you to Spand and Chudori's recent paper looking at Ophiuchus, where we do seem to find that some cores, so they were able to do a multi-component fit and find that you have dense cores with very narrow line widths at a particular velocity. And in some regions, that velocity is offset from kind of the lower intensity, broader component coming from the cloud. So that's in Ophiuchus. Certainly you can see in some regions where, sometimes the cores do appear to be offset from nearby environments, but that looking at over multiple filaments and what the offsets are, we still are working on.
So we have a question here that's, part of it is the question you just answered, but in addition, are the cores localized to fibers when they exist?
You mean like as in when they form? So I think the consensus, and certainly what we see, I think, in the dense gas is that the cores are found within these larger structures. You do have regions where you have cores that are offset from maybe these larger structures and filaments, but how the cores relate to the fibers, I think is still something that, figuring out, do the fibers form first and then the filaments, is it kind of like a sweeping up of fibers into a larger filament, or does the filament form and then kind of fray into fibers, is still a question. So how the cores fit into those two regimes is something that I think we can start to try and answer, but I don't have an answer for that right now.
Okay, and one final question. Do you ever find optically thick ammonia 1-to-1?
So we do not. At our resolution, I believe we do not. Overall, I mean, we may have regions where the overall opacity of the line is greater than 1, but because it's spread into the multiple hyperfine components, we never have an optically thick transition. Just trying to think. I think towards Orion, at least in the center, we do have regions where the line becomes really challenging to fit, but that's more because of a very broad underlying component. So I think with our resolution, we don't usually we haven't found optically thick 1-1 emission that I can remember.
We have time for one or two more questions, which we have. How could the filament's magnetic field tie into core stability?
That's a great question. So I actually is something that I'm interested in investigating. So I do have a student working on understanding the, looking into understanding the orientation and angular momentum of cores relative to the local gravitational or the local magnetic field based on, bringing in data from Planck or perhaps the Bistro surveys. So definitely, if you had a magnetic field in the filament, you would that would be could be an extra source of support depending on how it's oriented, and so would tie into the filament and core stability there. So we definitely there are some surveys where we are going to have that data, and I know that the Bistro survey has been working on the polarization measurements from the continuum and understanding the importance of the magnetic field there. So I think that's definitely a great direction to go.
Okay, finally, a comment and another question. The comment is about the question of the opacity of the ammonia transition. In L183, it is optically thick, about 20. And then a final question, I would like to know how I can get the full data.
Yes, the full data. So we have, I should have put this on the link. Our initial data is on the Dataverse, and as our papers are published, we will add more data sets there. If there is data on a region that you would like that isn't yet published, feel free to get in touch with myself or Jaime Pineda, and we can work. We're happy to work with people to share data before we've had the team published, as long as it's yeah, please get in touch if you would like the data.
Okay, thank you very much, Rachel. There are
you.
several comments that came in as compliments, and thanks to everyone who attended the webinar, and we look forward to seeing you in 2 weeks. Okay, Paul, are we done?